Alright, y'all, my name's Vaughn Bell. I was the Group 1 reporter for Lab 2, which was the bomb calorimeter. So, a little introduction. The PAR oxygen bomb calorimeter is used to measure heat produced by combustion of either a solid or a liquid, whichever your fuel sample is, as well as analyzing the products of combustion. This type of calorimeter is widely accepted for these types of for heats of combustion measurements because of its accuracy and its ease of use. Upon ignition, heat is transferred from the surface to the surroundings, and this temperature change is recorded using the DAC-View software, which we have hooked up to a computer. And then the biggest thing about this experiment is the first law of thermo, where the heat of combustion first law of thermo, in this process, it's a constant volume process. So pressure is not going to change as well inside of the calorimeter. So in this equation, Q is equal to the heat of combustion, MCD is the thermal capacitance, which is basically a measure of how much heat is needed to heat something up per 1 degree Celsius. And delta T is obviously our change in temperature from prior to ignition and after ignition. So then the objective of this lab was to become familiar with the physical principles, procedure, and analysis techniques associated with the bomb calorimeter, determine the thermal capacitance of the calorimeter, and the gross heat of combustion of the benzoic acid sample and the miconite sample. So the apparatus here, so let's see, the big one, 7 is a water stirrer. We need that because the temperature needs to be evenly distributed throughout the system. 2 is blown up right over here. That is the detail of the bomb with, let's see, A being the inlet check valve, B being the pressure release valve, C are the 2 electrode terminals, D is the crucible, F is the ignition wire, and 2 is the housing, and 3 is the lid ring, locking ring. And then 6 on the left view is the thermocouple that we use to measure the temperature change. So for the benzoic acid, you can see it around 23.2 was where it combusted, and it rose it was I think it came out to about 25.8 or 9-ish, and that's where it peaked off at. So with the initial temperature being 22.9 right before combustion, and the final temperature being 25.9, we got a temperature change of 3 degrees Celsius, and the ignition wire consumed was 7.4 centimeters. So in this experiment, actually, we had some issues with the benzoic acid sample. It did not combust, and the wire actually fused to the sample itself. So this data was provided per a different lab group. So there's a little bit of uncertainty with this, but for now, this is what we have for the benzoic acid sample. And then the data analysis on that, the heat of combustion according to the benzoic acid sample itself is 26.454 millijoules per kilogram. And then, so since we know the heat of combustion of the benzoic acid, we can find the thermal capacitance of the calorimeter by that equation right there, which ends up being 8.818 millijoules per kilogram. But in all those calculations, you have to account for the ignition wire consumed, which is that equation down there, Q total. The total combustion heat was equal to the heat of combustion from the acid and from the wire itself, with the wire heat of combustion being about 0.0712 kilojoules. So the total heat of combustion for this came out to be about 26.525 kilojoules for the benzoic acid. Then for the micanite, doesn't look as pretty, but started out at about 22.5 degrees Celsius and it finished at 23.6. So we only had a temperature change of 1.1 degrees Celsius and less ignition wire was consumed. And for this one, since we already know the thermal capacitance of the calorimeter, we could solve for the heat of combustion of the micanite itself, which is 9.6998 megajoules per kilogram. But like I said, you still have to account for the ignition wire, and all of that being accounted for came out to 9.764 kilojoules. So as you can see, the difference between the benzoic acid heat of combustion and the micanite heat of combustion is very large, given that the benzoic acid is an actual fuel and micanite is a piece of candy. And then, like I had said earlier with the sources of errors, our rubber band popped off during the benzoic acid and there was no combustion actually. And for the micanite, the rubber band didn't break off, but it did detach. We had to put it back on there, so that is a possible source for why the micanite graph doesn't look as pretty compared to this graph. So yeah, these are my sources, and y'all got any questions?